So now in section 4.6, we're going to use what we've learned in the previous sections about exponential and logarithmic functions to try and solve exponential and logarithmic equations. Now these are going to be types of equations where our normal tools for solving an equation, multiplying or dividing both sides of the equation by some real number, adding or subtracting by some real number, taking square roots, all these different types of things that we're used to doing will not help us in solving the equation, right? So we're trying to solve equations like this, where x is either the exponent, right, where what we're trying to solve for is an exponent, or where x is inside some kind of a logarithmic function. Before we start trying to solve these, let's talk about some properties of logarithmic and exponential functions that are going to help us along the way. First of all, we have the one-to-one property of exponential and logarithmic functions. These are one-to-one functions because, as we've said, they have inverses. They're inverses of each other, in fact. And so this leads us to the following property. We have that for any a, again, we can assume here that a is greater than 0 and not equal to 1. We have that a to the x is equal to a to the y if and only if x equals y. So if we have this equation where a to the x is equal to a to the y, we can conclude that x has to equal y and vice versa. If we know that x is equal to y, then we can, in a sense, exponentiate on both sides, raise both sides of the equation, or raise some fixed power a to each side of the equation, and it will still be equal. Similarly, log base a of x is equal to log base a of y if and only if x equals y. It's really important that the bases match here. It has to be the same base on both sides of the equation in order for this property to hold. Another helpful property is just the definition of a logarithm. Remember, we started off by saying that log base a of x is equal to y if and only if the base a raised to the other side of the equation y gives you x, gives you what's on the inside. This can help us as well. Now let's talk about the properties of logarithms. So I only put the power property that we talked about in the last video, that log base a of x to the y power is equal to y times log base a of x. But there were the other properties that we've seen too, which sometimes might come in handy. For instance, we had the multiplication property, which said log base a of x times y is equal to log base a of x plus log base a of y. Right, you can break up multiplication on the inside as addition on the outside, and similarly for the quotient property. And finally, we have this inverse property of logs. Because logs and exponential functions are inverses of each other, log base a of a to the x is always going to equal x, and a raised to the log base a of x is going to be equal to x as well. So we're going to use these to help us solve these various different types of equations. All right, let's start here. Solve for 2 to the x power is equal to 32. Well, the first thing I'm going to do, because I have a 2 to the x on one side of the equation, and on the other side of the equation I have 32, which happens to be a power of 2, I'm going to rewrite that right-hand side as a power of 2. 32 is 2 to the 5th power, because it's 2 times 2 times 2 times 2 times 2. And now what I can do is I can use the one-to-one property, which says that if you have a to the x is equal to a to the y, then x has to be equal to y. In this case, 2 to the x is equal to 2 to the 5, so in a sense we can sort of cancel out these bases and conclude that x is equal to 5. Alright, let's try another one. We have ln of x minus ln of 3 is equal to 0. Alright, well, I'd like it so that I can use the one-to-one property again, this time with logs, this one here. So if I can rewrite this with a log on each side of the equation with the same base, and I can, right, I can add ln of 3 to both sides. And I can rewrite this equation as ln of x is equal to ln of 3. And now, once again, I can use that one-to-one property, this time of logarithms, to conclude that whatever's on the inside here has to be equal. So x has to be equal to 3. Alright, for example 3, we have 1/3 to the x power is equal to 9. Right off the bat, this doesn't seem like something we'll be able to use the one-to-one property of, because in order to use that one-to-one property, if you're trying to solve for x, the exponent, you would need the bases to be the same. And so the question is, can I rewrite this in a way that these are two different functions with the same base, or two different powers with the same base? And it turns out I can, because remember that 1/3 is the same thing as 3 to the negative 1 power. And so 1/3 to the x would be 3 to the negative 1 power to the x. And similarly, on the other side of the equation, I could rewrite 9 as 3 raised to the 2nd power. Now, using my normal exponent rules, I can rewrite this by multiplying my two exponents. So the left-hand side would become 3 to the negative 1 times x, or 3 to the negative x power, is equal to 3 to the 2nd power. And now I can use that 1-to-1 property because I have two powers with the same base that are equal to each other. So by the 1-to-1 property, I can conclude that negative x is equal to 2, and thus x has to be equal to negative 2. Alright, so all three of these first examples have used that 1-to-1 property. Let's look at a few more examples. E to the x is equal to 7. If I wanted to use the 1-to-1 property here, I'd need to rewrite 7 as e raised to some power. But e is an irrational number. It's 2.718 blah blah blah, never repeats. So if I wanted to rewrite the whole number 7 as e raised to some power, that power is going to be pretty messy. So I don't think the 1-to-1 property is going to help us here. So let's go back and think, which one of these properties can I use? Well, it might be useful here to try to use, let's say, this one down here. We know that log base a of a to the x is always going to be equal to x, and similarly a to the log base a of x is going to be equal to x. So what we have is we have an x that's sort of trapped in an exponent. So if we wanted to get that x out of the exponent, I could use this first equation here, and I can know that log base a of a to the x is equal to x, which means I have a base of e here. So if I take log base e, that is natural log of both sides of the equation, which I can do again because of the 1-to-1 property, I'd have ln of e to the x is equal to ln of 7. And now, because this is a log, ln just means log base e. So log base e of e to the x, these two in a sense cancel each other out and leave you just with x is equal to ln of 7. What is ln of 7? I don't know, it's a number, right? I would probably use a calculator to try to figure out exactly what that is. But I can't really write what ln of 7 is because it will probably also be an irrational number, so it's the most correct way to express this is just plain ln of 7. Alright, similarly for number 5, we have an x that's sort of trapped inside a log function, and we want to get it out because we want to solve for x. So if we go back here, now let's use the second equation here. This says that a raised to the log base a of x is equal to x. So if you wanted to get an x out of the inside of a log function, we just use this little trick of exponentiating on each side of the equation. So my base here is e. Remember, ln means base of e. So what we're going to do is raise e to each side of the equation. Okay, so I'm going to do e to the ln of x is equal to e to the negative 3. Again, this is allowed because of that 1-to-1 property. And now, e to the ln of x, well, e and ln are inverses of each other. So just like before, this e raised to the ln power, they cancel each other out, and you're just left with x is equal to e to the negative 3. Or if you wanted to, you could rewrite this as x is equal to 1 over e cubed, because a negative exponent is the same thing as bringing it into the denominator. So we get 1 over e cubed as our value for x. Again, e is an irrational number, so this is not going to be something nice. It's not going to give you a whole number, but that's the most exact way we can express that solution. All right, let's try this again. We have log of x is equal to negative 1. What is our base here? It just says log. So you have to remember back in the last video, or maybe even the one before, we'd said that if we don't see a base written, we can assume it's base 10. I didn't draw that very well. We assume it's base 10. Okay, so this is log base 10 of x is equal to negative 1. And just like in example 5, we have an x stuck inside a log function, and we're trying to get it out. So what we'll do is we'll raise this time our base is 10, to each side of the equation. This is going to allow us to break that x out of the parentheses. So we have 10 raised to the log of x is equal to 10 to the negative 1. Now because we have a base of 10 raised to a log base 10, they cancel each other out, and we're just left with x is equal to 10 to the negative 1. Or we could rewrite this as x is equal to 1 over 10 to the first power, or just plain 1 over 10. All right, one more. We have log base 3 of x is equal to 4. I want to get that x out of the log function, so this is just like numbers 5 and 6. What I'm going to need to do is raise, this time my base for the log function is 3. So raise 3 to each side of the equation. And we get 3 raised to the log base 3 of x is equal to 3 to the 4th power. Now that 3 log base 3 cancel each other out because they are inverses of each other, and we just get that x is equal to 3 to the 4th power. Or x is equal to 3 times 3 times 3 times 3. That's 9 times 9, so this would be 81. Okay. All right, let's just do a couple more examples. These get a little bit more complicated. So this time we have e to the negative x squared is equal to e to the negative 3x minus 4. Well, let's think back to our one-to-one examples from the beginning. We have two powers that are equal to each other, and they have the same base. So by the one-to-one property, we can conclude that negative x squared is equal to negative 3x minus 4. And solving for x is just as simple as solving this quadratic equation. It's quadratic because it's an x squared function, right? The largest exponent is x squared. And to solve a quadratic, we usually want to get everything on one side of the equation and 0 on the other side. So I'm going to add x squared to both sides. To get 0 is equal to x squared minus 3x minus 4. I could use the quadratic formula if I wanted to, but it's easier to factor if you can, so this one's factorable. 1 and 4 would work. I need it to multiply to negative 4 and add up to negative 3. So x minus 3 and x plus 1. And setting each one of these factors equal to 0 is going to give us x equals negative 1 and x equals 4. These are your two solutions. So this is the first time that in solving an exponential function or an exponential equation, we actually got two solutions. So negative 1 would work here and 4 would also work. All right, let's look at number 2. We've got 3 times 2 to the x power is equal to 42. Now my x is stuck in the exponent, so you should be thinking that this is similar to problem 4 on this last page here, right? We had an x stuck as an exponent. And the way that we solved that is we took the natural log of both sides. In other words, log base e of both sides to get rid of that base and leave me with just the exponent. So that's what I'm going to do here, but before I can do that, I really need to get that powered 2 to the x by itself. Right now it's 2 to the x times 3, so I can get rid of the 3 by dividing both sides by 3 to start with. Right, that'll leave me with 2 to the x on one side of the equation, and on the other side I get 14. 42 divided by 3 is 14. Now I'm in that same position that I was in number 4. I have 2 to the x is equal to 14. I want to bust out that x from the exponent. So to do that, what I'll do is take the natural log of, does it make sense to take the natural log of both sides? That's what I did here, but that's only because my base was e. So it made sense to take the natural log of both sides because the natural log is log base e. I have a different base here. Now my base is 2. So instead I'm going to take log base 2 of both sides. Right? So I'm going to take log base 2 of 2 to the x, and that will be equal to log base 2 of 14. So I just took each side of the equation and plugged it into the log function. The reason for doing this is that log base 2 of 2 to the x is just plain equal to x, And so we get that x is equal to log base 2 of 14. Now, log base 2 of 14 is some real number, but it's not going to be anything nice because you don't get 2 raised to some nice whole number power gives you 14. So it's okay to just leave this as log base 2 of 14. Just a couple more examples in this section. We have e to the x plus 5 is equal to 60. So just like before, it's going to make sense to try to get e to the x by itself before we use the trick from problem 4 over here. Right, when we had e to the x equals 7, we could just take ln of both sides. So let's get that e to the x by itself by subtracting 5 on both sides. So e to the x is equal to 55. And now to get that x out of the exponent, I can take ln of both sides. And again, we're using ln, log base e, because the base of my exponent is e. That's why we did log base 2 in the last example, because my base was 2. Now my base is e, so I'll take log base e, or ln of both sides. So I get ln of e to the x is equal to ln of 55. These cancel out, and I'm left with x is equal to ln of 55. It's not going to be a nice number, but it's still a solution. And finally, for number 4, we have ln of x cubed plus 4 is equal to 55. All right, first thing I'm going to do is get rid of that plus 4. So I'm going to subtract 4 on both sides to get ln of x cubed is equal to 51. Now, you might want to try to, get rid of that ln just like we did a couple pages ago by raising e to both sides. And you could, but what I'm going to do first is get rid of the 3 on the inside, get rid of this exponent using our different properties of exponents. Remember, we said you can always take a power that's inside a log and move it outside as multiplication. So this is 3 times ln of x is equal to 51, and this was just by the power property of logs. Now I can divide both sides by 3. So we have, let's see, oops, don't do that. We have ln of x is left on the left-hand side, and on the right we have 17. 51 divided by 3 is 17. And now what we can do is raise e to both sides of the equation. This is using the 1-to-1 property. And the reason we're choosing e is because our log is ln. Right? ln means log base e. So I raise e to the ln of x, and that'll be equal to e to the 17. All right, now e to the ln, they cancel each other out, and we're just left with x is equal to e to the 17. Okay, that's a very big number. So we'll leave it as just e to the 17 here. We'll do some more examples in class.